In the darkness of our galaxy, there is a neutron star so quiet and so strange that it defies everything we thought we knew. This object is Calvera, the silent star that shouldn't exist at all. Tonight we'll uncover why its very presence is a cosmic mystery. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what's the strangest star you've ever heard of? Thank you for watching. Now, let's begin. Calvera stands high in the northern sky, in the small constellation Ursa Minor, where the pattern of familiar stars traces a quiet outline far from the crowded band of the Milky Way. On clear, dark nights, the Milky Way stretches as a pale, tilted band across the sky, marking the plane of the galaxy where most of its stars lie. Calvera's position is well away from this band at a galactic latitude of roughly plus 37 degrees, which means that the star sits far above the thin disk of stars, gas and dust that forms the main visible body of the Milky Way. Astronomers use galactic coordinates to describe such locations, a system that measures positions on the sky in longitude and latitude with respect to the galactic plane and the direction of the galactic center, in much the same way that geographical longitude and latitude describe locations on the surface of Earth. Galactic latitude is measured as an angle above or below the plane that defines the midline of the Milky Way's disk. A latitude near zero marks an object that lies close to that midline where the sky is rich in overlapping star fields and dust clouds, while larger positive or negative values mark objects that are seen higher above or below the disk. Calvera's latitude near plus 37 degrees places it well into the region that astronomers call the galactic halo, where stars are scattered and the sky is thinner in bright foreground light from the disk. When astronomers look toward the patch of sky where Calvera resides, they see a relatively sparse field of ordinary stars with no obvious bright nebulae or thick dust lanes to mark a busy region of star formation. The constellation Ursa Minor itself is a modest pattern, best known for the presence of Polaris near the tip of its tail, but Calvera does not stand out in visible light. In optical images, the field looks almost anonymous, one faint star among many. Calvera reveals itself instead as a source of soft X-rays detected with X-ray observatories that survey the sky at much higher energies than those visible to the human eye. In catalogues, it appears first as an X-ray source with a position measured precisely enough that telescopes in other bands can be pointed at the same coordinates. The fact that this X-ray source sits at such a high galactic latitude is the first clue that it inhabits an unusual region for a young neutron star. Most massive stars are born in the galactic disk, where gas is dense enough to collapse into new stars, and most core collapse supernova explosions that leave behind neutron stars also occur close to the plane. The band of the Milky Way on the sky is therefore the region where astronomers expect to find many of the brightest and youngest neutron stars and pulsars. By contrast, Calvera's position well above this band immediately suggests a very different environment, one that is more typical of old stars in the halo than of recently born stellar remnants. To interpret this high latitude in a more physical way, astronomers combine it with estimates of the distance to the star. A galactic latitude describes a direction, not a height by itself, but if the distance to the object is known or constrained, that angle can be converted into a perpendicular height above the galactic plane. For Calvera, models of its X-ray emission and constraints on its brightness in other bands suggest that it lies not in the very local neighbourhood, but at a distance of at least several thousand light-years, and possibly more. At such distances, a latitude of around plus 37 degrees corresponds to a location thousands of light-years above the plane of the Milky Way. Even if the distance turns out to be nearer the lower end of current estimates, Calvera still occupies a region far from the thin layer where most of the galaxy's gas and young stars reside. This high location also means that the line of sight toward Calvera passes through relatively little interstellar gas and dust, so the X-rays that emerge from the star are less absorbed than they would be for an otherwise similar object seen through the thick disk. Observers can therefore study its soft thermal emission with relatively little obscuration, which is one practical reason why the star's X-rays are so clearly detected. The view of Calvera from Earth is therefore shaped by two aspects of geometry. First, the orientation of the galactic plane on the sky causes the main disk of the Milky Way to appear as a bright ribbon, so any object above that ribbon sits in a comparatively dark background. Second, the combination of latitude and distance for Calvera lifts it out of the dense layers of gas and dust, allowing more of its emitted X-rays to reach Earth-based detectors. When astronomers map the distribution of neutron stars and pulsars, they usually find the densest concentrations in directions near the plane and around the galactic center, where massive star formation has been strongest over cosmic time. Calvera's position stands apart from this pattern. In maps of galactic coordinates, it appears in the upper reaches of the diagram high above the midline, occupying a space where only a small fraction of known neutron stars are currently catalogued. This does not by itself tell the full story of its origin or motion, but it establishes the basic observational fact that any explanation of Calvera must take into account the star is a neutron star that now sits far above the main disk of the Milky Way in the realm of the halo, yet it shows timing and emission properties that point to a relatively young age. In this first outermost view, Calvera is simply one compact remnant plotted on a galactic map, yet its coordinates already mark it as a star whose present location is unusual among objects of its kind. Across the Milky Way, neutron stars arise as the compact dense remnants of massive stars that end their lives in core collapse supernova explosions. These massive stars are born mainly in the thin stellar disk of the galaxy, where cold interstellar gas gathers into clouds dense enough to fragment and form new stars. The thin disk is a flattened structure, a few hundred parsecs in thickness, filled with spiral arms, molecular clouds, and bright star-forming regions. Inside these regions, the most massive stars live short lives, burning their nuclear fuel rapidly before their cores collapse under gravity. When that collapse takes place, the outer layers of the star are blown outward in a supernova, while the inner core is compressed into a neutron star, an object with a mass comparable to that of the Sun, squeezed into a sphere only a few tens of kilometers across. Once formed, the remnant carries away most of the angular momentum and magnetic flux from the original star, so it tends to rotate rapidly and possess a strong magnetic field. These features govern its later behavior, but its origin remains tied to the environment of the thin disk where its progenitor star was born. The Milky Way also contains a thicker stellar component often described as the thick disk, and an extended halo of old stars and dark matter that surrounds the disk and bulge. Star formation in these regions is much weaker than in the thin disk, and the supply of cold gas is relatively limited. As a result, most ongoing massive star formation and most core collapse supernovae are concentrated close to the galactic plane. Surveys of known neutron stars and pulsars reflect this pattern. When astronomers plot their positions in galactic coordinates, a strong concentration appears near zero latitude, tracing the same flattened plane that the Milky Way band draws across the sky. As latitude increases, the surface density of known young neutron stars drops, because fewer of their progenitor stars are formed at large heights above or below the plane. Some old neutron stars can migrate to higher latitudes over long times through a combination of orbital motion and gravitational interactions, but very young remnants are expected to remain close to the layer where they were created. An important detail in this picture is that a neutron star does not simply settle quietly into place when its core forms. During the supernova explosion, slight asymmetries in the ejected material and in the core collapse can impart a recoil, often called a natal kick to the remnant. This kick can give the newborn star a space velocity of hundreds of kilometers per second relative to its surroundings. The direction and magnitude of the kick vary from event to event, so over time neutron stars spread out from their birthplaces. Many remain confined within the thin disk, moving in orbits that keep them relatively close to the galactic plane, while some are thrown onto paths that carry them into the thick disk or the halo. Even with these kicks, most neutron stars formed recently are still found at modest heights above or below the plane, because the galaxy's gravity keeps their orbits bound, and the timescale for travelling far into the halo is long. This makes the vertical distribution of neutron stars a sensitive tracer of their ages and of the kicks they receive. For a remnant that is only a few 100,000 years old, there is limited time to travel a large vertical distance, so a location very far from the plane implies either a particularly strong vertical kick, an unusual birth site at high latitude, or a longer time scale than the characteristic age might suggest. In broad population studies, astronomers therefore compare the observed heights of neutron stars and pulsars above the plane, with models that include typical kick speeds and the galactic gravitational potential. These models can reproduce the general trend seen in surveys with most young objects near the plane, and a tail of older or faster-moving stars at higher latitudes. They also show that truly young neutron stars found deep in the halo should be rare. Against this background, Calvera's location stands out. It shares the basic origin story of other neutron stars as the compact remnant left by a core collapse explosion, yet it now appears at a latitude that places it far above the thin disk where its progenitor would most likely have formed. The expected path for a massive star is birth in a spiral arm near the galactic plane, a brief, luminous life, a collapse into a neutron star, and then a journey that keeps the remnant's orbit linked to the disk for a long period. Calvera instead is observed in a part of the sky more typical of old halo stars. This does not immediately define its history, because the combination of kicks and galactic orbits can produce a wide range of trajectories, but it means that any detailed account of its past must work within the wider pattern set by the galactic neutron star population. The broader statistics show a strong correlation between youth and proximity to the plane, so a seemingly young neutron star at high latitude is unusual. Calvera occupies precisely this category. It is one example, perhaps among a small minority, of a compact remnant that now resides high above the main star-forming layers of the Milky Way. In this context, its galactic position is not just a coordinate on a map, but a constraint on the kind of path the remnant must have followed since its birth, and on the environment in which its progenitor star once lived. In the region of sky around Calvera, deep radio observations reveal a broad and faint ring of emission that circles the neutron star at high galactic latitude. This structure, now catalogued as the source G 118.4 plus 37.0, appears in low-frequency maps from the LOFAR 2-meter sky survey as a diffuse, almost circular band of radio brightness that spans nearly 1 degree across the sky. Its surface brightness is low, so that in earlier, shallower radio surveys it does not stand out as a striking object, but with improved sensitivity and resolution, the ring emerges as a coherent structure whose centre lies only a modest angular distance away from Calvera's position. Astronomers measure this separation as a few arc-minutes small compared with the overall diameter of the ring, which suggests that the neutron star sits close to the geometric middle of the diffuse emission when projected on the sky. Carefully processed images show that the ring has an inner radius of roughly 14 arc-minutes and an outer radius of about 28 arc-minutes, so that its thickness and shape resemble a hollow shell. Within this shell, the radio brightness enhances relative to the more uniform background of the halo sky, yet it remains much weaker than the bright filamentary supernova remnants that are found nearer to the galactic plane. The detection of such a ring at high latitude is in itself noteworthy because diffuse radio structures in the halo are uncommon and often difficult to classify. In the LOFAR maps, the ring encircles a region that also contains an earlier known X-ray source, identified as a patch of diffuse high-energy emission. This layered view with a radio shell on large scales and a softer X-ray patch inside hints at a complex local medium rather than an isolated point source. To understand the nature of the ring, astronomers examine not only its shape and brightness, but also its spectrum. By comparing images taken at different radio frequencies, they can infer how the intensity of the emission changes with frequency. For a shell that is a remnant of a supernova explosion, the radiolight is usually dominated by synchrotron radiation, produced when fast electrons spiral in magnetic fields. This process tends to give a steep spectrum in which the brightness drops rapidly as the observing frequency increases. For the ring around Calvera, the available data indicate a spectrum consistent with non-thermal synchrotron emission, which supports the idea that it is not a simple region of ionized gas lit by nearby stars but a relic of some energetic event. The ring's large angular size implies that if it lies at a distance similar to that of Calvera, its physical diameter is many parsecs comparable to those of other known supernova remnants at intermediate ages. A diameter of this scale, coupled with its low surface brightness, fits the picture of an expanding shell that has grown large and faint as it interacts with a relatively tenuous interstellar medium. The surrounding environment at high galactic latitude provides exactly such a setting, with low gas density and few dense clouds to confine the expansion. In addition to radio data, observers have obtained optical images in narrow bands centered on emission lines, such as hydrogen alpha, which often glow in the shock fronts of supernova remnants, where fast shocks excite and ionize the gas. In the case of the Calvera ring, deep optical exposures show no bright shell that traces the radio structure, though they reveal a small and faint knot of emission inside the ring that may or may not be related. The lack of strong optical emission is consistent with a shell expanding in a low-density medium where shocks can be relatively weak in terms of line emission, while still producing synchrotron radio brightness. X-ray maps of the wider region show diffuse high-energy emission near the ring as well interpreted as non-equilibrium ionized plasma, which points again to a history of heating and shock activity in the local gas. When all these pieces are combined, the radio ring, the diffuse X-rays, and the presence of Calvera at its projected center, astronomers consider several possible interpretations. One is that the ring is an ionized gas region created by the ultraviolet radiation from some massive star, but the lack of a clear central ionizing source and the steep radio spectrum disfavor this. Another is that the ring belongs to a class of objects known as odd radio circles, distant extragalactic phenomena that also appear as hollow radio shells. However, the positional coincidence with a known neutron star and with X-ray emitting plasma, as well as differences in typical environment and distance, make this explanation less natural. The remaining and currently favored interpretation is that the ring is a supernova remnant located in the galactic halo and physically associated with Calvera. In this picture, the radio shell marks the swept-up boundary of the explosion that created the neutron star, now expanded to a large faint bubble in the thin halo gas. The offset between the geometric center of the ring and Calvera's current position can then be understood as the result of the neutron star's motion since birth, combined with possible asymmetries in the shell's expansion. The rarity of supernova remnants at such high galactic latitudes adds importance to this identification, because if confirmed, it would make G118.4 plus 37.01 of the few known shell remnants in the halo. For the present narrative, the key fact is that Calvera does not float alone in an empty region of sky. It appears instead at the center of a broad circle of faint radio emission, and near a patch of diffuse X-rays, suggesting that the neutron star resides within a larger structure that records the history of the explosion that once shook this part of the halo. In this outer ring, the story of Calvera is written not only in the pulses of the star itself, but also in the dim extended glow that still outlines the space that its supernova carved from the surrounding medium. The region that surrounds Calvera is filled not with bright clouds and dense gas, but with a very thin medium of ionized gas magnetic fields and diffuse high-energy emission. At the height above the galactic plane where Calvera resides, the interstellar medium is sparse with average densities that are much lower than those found in the thin disk. Instead of crowded molecular clouds and bright star-forming regions, there is a mixture of warm and hot gas that has been shaped by past supernova explosions and by the outflows of earlier generations of stars. In this halo environment, the boundaries between distinct structures tend to be soft. Shells, bubbles, and filaments overlap and blend into one another, while the overall gas pressure remains low compared with the inner regions of the galaxy. Within this context, the large radio ring around Calvera can be seen as one element of a more extended complex that also includes high-energy plasma inside the shell. X-ray observations of the area show diffuse emission spread across a region that is comparable in size to the radio ring, but offset in detail with patches of brighter and fainter emission that hint at a turbulent and uneven medium. The spectrum of this diffuse X-ray light can be modelled as emission from a hot optically thin plasma that is not yet in ionization equilibrium. Non-equilibrium means that the ionization states of the atoms and ions in the gas do not match those expected for a plasma that has had a very long time at a fixed temperature and density. Instead, the gas appears to have been heated relatively recently, so that the electrons and ions are still adjusting to the new conditions. This is a common signature in the interiors of supernova remnants, where a shock wave from the explosion heats the gas rapidly, and then leaves it to cool and recombine over longer timescales. In the region around Calvera, the presence of such non-equilibrium plasma suggests that the local interstellar medium has been disturbed by at least one significant energetic event in the past, consistent with the idea that the radio ring is a shell blown by a supernova. Because the surrounding gas density in the halo is low, the shock from that explosion can travel a long way before slowing to a gentle expansion, which explains how a shell can reach a large diameter while still remaining relatively faint. The hot plasma in the interior then fills much of the volume inside the ring, providing a reservoir of thermal energy that glows in X-rays even as the shock front loses energy and the shell becomes more tenuous. The detailed shape of the diffuse X-ray emission around Calvera does not follow the radio ring exactly, which indicates that the distribution of hot gas is more complex than a simple filled sphere. There may be regions where the shock has broken out into even lower density surroundings regions, where the gas has cooled more efficiently, and regions where magnetic fields and pre-existing clouds have deflected or slowed the flow. All of this structure arises within an environment that on average remains very thin compared with the gas in the galactic disk. For the neutron star itself, this environment sets the external conditions under which its own outflows and radiation interact with the surroundings. A rotation-powered neutron star can drive a wind of relativistic particles and magnetic fields outward, carving a smaller bubble inside any larger remnant. In many young pulsars, this process creates a bright pulsar wind nebula, where synchrotron radiation from high-energy particles fills the interior and forms vivid structures. In the case of Calvera, no such bright nebula has been detected, which already hints that the balance between the power of the wind and the pressure of the surrounding gas differs from that of the most luminous young systems. The ambient medium here is so rarefied that a wind may expand more freely, reaching lower densities, where its radiation becomes extremely faint. Alternatively, the intrinsic power carried by the wind may be modest, compared with that of more energetic pulsars, so that any nebula is intrinsically dim. In either case, the absence of a strong compact nebula focuses attention on the diffuse structures on larger scales, the radio ring and the hot plasma as the main visible traces of the energetic history of this region. The pressure of the hot gas in the interior of the ring, coupled with the ram pressure of any remaining expansion, and with the very low density of the surrounding halo, helps shape the long-term evolution of the remnant. Over time, the temperature of the plasma gradually declines as the gas radiates energy in X-rays and other bands. The ions recombine, the shock front slows, and the shell blends more fully into the background medium. During this stage, the neutron star moves through an environment that is still somewhat overpressured relative to the remote halo, but far more tenuous than the interstellar medium in the galactic plane. The density of ambient gas influences the rate at which the neutron star sweeps up material and the strength of any bow shock that can form ahead of it if its motion is supersonic. In the thin halo gas around Calvera, the mean free path between particles is long, and the Mach number of the star's motion, which compares its speed to the local sound speed, may place it in a regime where any shock is broad and faint. Observations at X-ray and radio wavelengths so far do not reveal a sharp bow shock or a narrow comet-like tail features that are sometimes seen in pulsars racing through denser parts of the interstellar medium. Instead, Calvera seems embedded in a broadly disturbed but visually quiet bubble of gas and plasma, where most of the dynamical history is recorded in low surface brightness structures. This local environment forms an intermediate layer in the story of the neutron star. On large scales, the halo and the galactic context set the overall backdrop. On the scale of the remnant, the radio ring and diffuse hot plasma mark the footprint of an energetic explosion in the recent past. Within that footprint, the conditions of low density, modest pressure, and uneven temperature define the immediate surroundings in which Calvera now rotates and cools, shaping how its radiation escapes, and how any outflow interacts with the gas on its way out into the wider halo. In many well-studied young neutron stars, the space immediately around the remnant is marked by a bright pulsar wind nebula, a region where a steady outflow of highly energetic particles and magnetic fields from the star interacts with the surrounding gas. This wind carries away part of the rotational energy of the neutron star and can inflate a bubble of relativistic plasma inside the expanding shell of the supernova remnant. In X-ray and radio images, such nebulae often appear as luminous knots, arcs, and diffuse halos that sit close to the pulsar itself, sometimes with a torus and jet structure that traces the geometry of the magnetic and rotational axes. The Crab Nebula and several other famous objects in the galactic plane show this behavior, with the central pulsar embedded in a bright compact synchrotron nebula. These examples stand as prototypes for the interaction between a powerful young pulsar and its immediate environment. Against this backdrop, astronomers examining deep images of the region around Calvera find a striking absence. Despite sensitive searches in X-rays and radio, there is no clear sign of a compact high-surface brightness nebula centered on the neutron star. The X-ray emission from Calvera is dominated by the point-like thermal component from the star's surface, with only very limited room in the data for any extended non-thermal emission. Radio observations likewise do not reveal a small bright synchrotron source at the star's position. Instead, the detectable radio emission is concentrated in the much larger faint ring that extends on scales of tens of arc minutes, interpreted as the shell of the older supernova remnant. The area immediately around the pulsar appears comparatively clean, with no obvious structures that would mark a strong confined pulsar wind nebula. This lack of a bright nebula does not mean that Calvera has no wind or no interaction with its surroundings. A rotating neutron star with a measurable spin-down rate must lose energy, and a significant fraction of that energy is expected to go into particle outflows and electromagnetic waves. However, the form in which that energy manifests itself on observable scales depends on several factors, including the total spin-down power, the density and pressure of the ambient medium, and the geometry of both the pulsar's magnetic field and its motion through space. In the thin halo gas where Calvera resides, the external pressure is low, and the density of particles available to be swept up by a wind is small. Under such conditions, a pulsar wind can expand more freely, reaching lower densities before it is confined, which reduces the surface brightness of any resulting nebula. The synchrotron radiation from relativistic electrons and positrons then spreads over a larger volume, lowering the intensity at any given point, and making the nebula difficult to detect against the background. In addition, Calvera's spin-down power, while sufficient to produce the observed thermal emission and to sustain its rotation as a pulsar, may be modest compared with the most energetic young pulsars that power the brightest wind nebulae. Population studies show that only a subset of neutron stars have the combination of high spin-down power and dense surrounding medium that yields luminous, easily imaged nebulae. Many others likely drive winds that are either weak, extended, or both, and therefore contribute to the diffuse high-energy background rather than to obvious compact sources. Calvera appears to fall into this quieter category. The environment that is described by the large radio ring and the non-equilibrium X-ray plasma provides some additional context. The radio shell suggests that the supernova explosion that created Calvera occurred long enough ago for the remnant to expand to a large radius, and in a medium thin enough that its surface brightness is now low. Inside that shell, the hot plasma traced by X-rays represents gas that has already been processed by shocks and is evolving toward equilibrium. Within this bubble there may have been a young pulsar wind nebula in the earlier stages of evolution, when the neutron star's spin-down power was higher and the internal pressure of the remnant was greater. Over time, however, as the pulsar slows and the remnant expands and cools, the conditions that sustain a bright nebula change. The termination shock, where the pulsar wind is slowed and compressed by the ambient medium, can move outward and weaken while the particle population inside the nebula loses energy through radiation and adiabatic expansion. The result is a faded, diffuse population of relativistic particles that blend into the broader interior of the remnant. In such a scenario, any remaining pulsar wind nebula around Calvera today would be faint and difficult to separate from the background plasma even in deep images. Observational limits from current X-ray and radio telescopes are consistent with this picture. They do not entirely rule out a low-brightness nebula, on scales smaller than the radio ring, but larger than the immediate point source, yet they place strong constraints on the luminosity and compactness of any such structure. For practical purposes, the immediate visual environment of Calvera is that of a lone point source seated within a large faint shell without the bright knotty structures that characterize some well-known young pulsar systems. This has consequences for how astronomers interpret the star's energy output. With no luminous nebula to serve as a calorimeter for the Pulsar wind estimates of the spin-down power and of the partition of energy between thermal emission magnetospheric radiation and particle outflows must rely more heavily on timing measurements and on comparisons with other pulsars of similar spin properties. On the spatial scales immediately surrounding the star, the dominant features remain the diffuse hot plasma and the radio ring of the old remnant, while the neutron star's own surface emission stands out as the primary observable signature against a largely featureless local background. A neutron star like Calvera is at the most basic level the compact remnant left behind when the core of a massive star collapses under its own gravity. The mass of the original star's core, which was once spread across a region roughly the size of a large planet or more, becomes compressed into a sphere only a few tens of kilometers across. In most well-studied systems, the total mass of the remnant falls somewhat above that of the Sun, while its radius is on the order of a few tens of thousands of meters, so that the average density reaches values far beyond those found in ordinary matter. In such an object, a volume the size of a sugar cube would contain an amount of material comparable to that of a large mountain. Gravity at the surface is extremely strong, many trillions of times stronger than at the surface of Earth, so that any particle or photon leaving the star must climb out of a very deep gravitational well. This extreme compactness shapes almost every aspect of neutron star behavior, from the way light is bent near the surface to the way the star spins to the strength of its magnetic field. The birth of a neutron star occurs in the violent environment of a core collapse supernova. When the core of a massive star runs out of nuclear fuel, it can no longer support itself against gravity. The core contracts rapidly, the density rises, and a new, more compact state of matter forms in which most atomic nuclei have been broken apart and protons and electrons have combined to form neutrons. The outer layers of the star are blown outward in the explosion, while the core, now too dense to be disrupted, remains as a hot, rapidly rotating neutron star. In the first seconds and minutes after its birth, this remnant cools rapidly by emitting neutrinos while its outer layers settle into a rigid crust and its intense magnetic field couples to the surrounding plasma. The details of this early evolution depend on the precise mass and composition of the progenitor star, but the end result is a compact object with a stable radius, a well-defined crust, and an interior that supports itself against gravity through the pressure of degenerate matter. Globally, a neutron star can be thought of as a single object, with a small radius, a large mass, and a strong magnetic field that typically ranges from billions to trillions of times that of Earth. The rotation period at birth may be only a few thousandths of a second, and although it lengthens over time as the star loses energy, many known neutron stars still spin many times per second. The combination of rapid rotation and a strong magnetic field gives rise to a magnetosphere, a region around the star filled with charged particles that move along magnetic field lines and emit radiation. In many neutron stars, this process leads to beams of radio waves and high-energy photons that sweep through space as the star rotates, producing the familiar pulsar signals detected on Earth as regular pulses. Regardless of the details of this magnetospheric activity, the core properties of the neutron star remain the same: a fixed mass and radius, a very high surface gravity, and a small hot surface that emits thermal radiation as the star cools over hundreds of thousands to millions of years. For Calvera, observations do not yet pin down an exact mass or radius, but they place the star firmly within this general class of compact remnants. Its X-ray spectrum and timing behavior identify it as a neutron star rather than a white dwarf or a black hole, and its emission is consistent with a surface whose size is comparable to that of other neutron stars. When astronomers model the soft X-ray emission from Calvera with atmosphere models appropriate for neutron star surfaces, they obtain effective radii that are in line with the few tens of kilometers expected for such objects once gravitational effects are taken into account. These models assume a global radius and mass within the usual neutron star range, and the resulting fits to the data do not require any extreme departures from those values. In this sense, Calvera appears to be a typical neutron star in its global structure, even if its surroundings and location are unusual. The gravitational field at Calvera's surface is so strong that light emerging from it is bent and redshifted. Photons that leave the surface lose energy as they climb away, so their wavelengths are stretched and their colors shifted toward lower energies. This gravitational redshift means that the temperature inferred from distant observations reflects not only the physical temperature at the surface, but also the effect of gravity on the emitted light. In addition, strong gravity causes light paths to curve, allowing an observer at a distance to see more than half of the star's surface at once. Regions near the far limb that would be hidden on an ordinary sphere can still be visible because their light is bent around the star on its way out. These global relativistic effects are important when interpreting the observed light curve of a rotating neutron star because they influence how hot and cool regions on the surface contribute to the observed brightness at different rotation phases. Another key global property is the star's moment of inertia, which measures how difficult it is to change its rotation rate. For a neutron star, the combination of high mass and small radius yields a moment of inertia much larger than that of any planet, so that even a small change in its spin rate corresponds to a significant exchange of angular momentum. As Calvera spins down over time, losing energy through electromagnetic radiation, and particle wins its rotation period, lengthens gradually, but its basic structure remains intact. In timing observations, the measured period and its rate of change encode information about the star's magnetic field and energy loss, while the overall stability of the rotation confirms that the object behaves as a rigid body on observable timescales. Calvera's place in the family of neutron stars can therefore be described in two layers. In the broader population, it is one member of a large group of compact remnants with similar masses, radii and surface gravities, all products of core collapse supernovae in the Milky Way. Its global physical parameters, so far as they can be constrained from observations, do not set it apart in any dramatic way. Instead, the aspects that make Calvera distinctive emerge when these shared properties are combined with its current location in the galactic halo, its thermal emission, and its timing characteristics. On the scale of global structure, however, it remains a neutron star in the usual sense, a dense compact star with a small radius, a strong magnetic field, and a deep gravitational well carrying the memory of a massive progenitor that has long since disappeared, while the remnant persists as a stable, slowly cooling object. Calvera makes itself known through soft X-rays, a band of light with energies higher than those of ultraviolet radiation, but lower than those of the hardest X-rays. In ordinary optical images, the field that holds Calvera looks unremarkable, a sparse scattering of stars with no bright nebula or cluster that would single out a compact object. It was only when X-ray surveys scanned this patch of sky that a source stood out as a steady, soft emitter, drawing attention in a band of energies where the human eye is blind. Follow-up observations with more sensitive X-ray telescopes confirmed that this source is compact, with no obvious extended structure at the angular resolutions probed, and that its spectrum is dominated by thermal emission. A thermal spectrum is one that can be described at least approximately by the radiation from a hot surface, with a single characteristic temperature, as opposed to a non-thermal spectrum that follows a different pattern, such as a power law, often produced by particles accelerated in magnetic fields. For Calvera, the shape of the spectrum across the soft X-ray band falls off smoothly in a way that suggests emission from a hot photosphere rather than from a population of highly relativistic particles. When astronomers first analyze the spectrum of Calvera, they sometimes use simple blackbody models, which treat the emitting region as an idealized surface that radiates according to temperature alone. These models can give a rough estimate of the temperature and the apparent size of the emitting area once the distance is assumed. In Calvera's case, a single blackbody fit indicated a temperature higher than those of some nearby thermally emitting, isolated neutron stars, and an emitting radius smaller than the full surface of a typical neutron star if the distance is taken to be modest. This combination suggested that either only part of the surface was contributing to the observed emission, or that more realistic atmosphere models were needed. As X-ray telescopes such as XMEM Newton Chandra and later NICER obtained higher quality spectra and pulse profiles, astronomers turned to models that treat the outer layers of the neutron star as a magnetized hydrogen atmosphere rather than an ideal black body. In these models, a thin layer of hydrogen sits above the dense crust and modifies the emergent spectrum through absorption scattering and the effects of strong magnetic fields on the motion of charged particles. The result is a spectrum that for a given surface temperature is broader and somewhat harder than a pure black body, shifting part of the emission toward higher energies. This means that when such an atmosphere model is fitted to a given observed spectrum, it often yields a lower effective temperature and a larger emitting radius than the corresponding black body fit, bringing the inferred size of the emitting area closer to that expected for a full neutron star surface. For Calvera fits that use a magnetized hydrogen atmosphere covering most of the star, possibly supplemented by smaller, hotter patches, provide a good description of the observed X-rays. The characteristic temperature inferred for the bulk of the emission is consistent with a neutron star that is still relatively young, cooling over a few 100,000 years since its birth, while the overall luminosity places it in the range of other thermally emitting neutron stars of similar age. At the same time, the spectrum of Calvera lacks a strong extended tail of emission at higher energies that would betray a dominant non-thermal component. Many young pulsars show such high-energy tails produced by particles accelerated in the magnetosphere, but in Calvera the thermal component appears to dominate the soft X-ray band. Any harder non-thermal emission must be weak compared with the thermal flux, or confined to energy ranges beyond those where the data are most precise. The softness of Calvera's emission is also reflected in the way its brightness declines at higher energies within the observed band. The flux drops steeply as energy increases, another signature that the emission arises from a thermal surface rather than from a broad power law distribution. The absence of strong line features in much of the spectrum, apart from a subtle absorption feature at a specific energy discussed later in connection with the pulse. Profile supports the use of continuum atmosphere models. However, the strong magnetic field near the surface can imprint modest deviations from a simple smooth curve, and detailed fits must account for these subtle effects. Another practical aspect of Calvera's spectrum is the relatively low interstellar absorption along the line of sight. Because the neutron star sits high above the galactic plane, the column of gas and dust between it and Earth is smaller than for a similar object embedded in the dense disk. This means that fewer soft X-ray photons are absorbed or scattered away before they reach detectors in orbit, allowing a clearer view of the intrinsic spectrum down to lower energies. When astronomers fit models to the data, they include a component that accounts for interstellar absorption, but the required amount is modest, reinforcing the picture of a halo object seen through a thinner blanket of interstellar material. The combination of a predominantly thermal spectrum, low interstellar absorption, and a compact emitting region allows Calvera to serve as a relatively clean example of a cooling neutron star seen mainly in soft X-rays. Unlike sources where strong magnetospheric emission or complex surrounding nebulae complicate the interpretation of the spectrum, Calvera presents a simpler case in which most of the observed flux can be traced back to the stellar surface itself. This does not mean that the surface is uniform. Evidence from the pulsations indicates that there are temperature variations across it. However, on average, the thermal component dominates, and the overall spectral shape can be captured by atmosphere models, with only a few key parameters: the effective temperature of the bulk surface, the size of the emitting area, the surface gravity set by the star's mass and radius, and the strength of the magnetic field in the outer layers. Within the broader family of isolated neutron stars, Calvera's thermal spectrum places it somewhere between the nearby, relatively cool objects sometimes grouped as the Magnificent Seven and younger, hotter, central compact objects found in the centers of some supernova remnants. Its temperature is higher than those of many very old thermally emitting neutron stars, but lower than those of the hottest young remnants. This intermediate position in temperature space aligns with timing estimates of its age, which suggest that it is neither extremely young nor ancient. The key difference lies not so much in the intrinsic nature of its thermal emission, as in the context Calvera is a rotation-powered pulsar, whose soft X-ray output is dominated by surface emission, yet it resides in the galactic halo and lacks the strong non-thermal signatures that often accompany such pulsars. The thermal X-rays that reveal Calvera therefore encode both the global properties of the star and the cooling history that has brought it to its present state, while offering observers a clear, steady signal against a relatively faint background. Across the sky, a small group of neutron stars forms a loose comparison set for Calvera. These are the thermally emitting isolated neutron stars objects, whose X-ray output is dominated like Calvera's by soft emission from their surfaces, rather than by bright nebulae or strong non-thermal tails. Among them, a particularly well-studied subset is often called the Magnificent Seven, a group of nearby radio-quiet neutron stars detected in soft X-ray surveys and later examined in detail. They share several features. They are isolated with no binary companions. They emit steady soft X-rays with spectra that can be modelled largely as thermal emission from their surfaces, and they show little or no strong non-thermal power law component in the energy range where they are best observed. In optical light, they are extremely faint, with only the nearest members detected as very weak bluish points, confirming that their emission at higher energies dominates their total output. These stars are relatively close to the Sun, lying within a few hundred light-years, so that their distances can be measured or constrained by parallax and by comparison of their X-ray fluxes with atmosphere models. Their positions on the sky are not confined to the exact mid-plane of the galaxy, but they do not reach the high galactic latitudes of Calvera. They sit in and near the local bubble, a region of hot, low-density gas that surrounds the Sun, and their soft X-ray emission is seen through columns of interstellar material that are modest but not negligible. In contrast, early studies of Calvera suggested that it might be one of the nearest known neutron stars because of its brightness and softness in X-rays combined with the lack of a bright optical counterpart. However, as more refined atmosphere models were applied, and as its pulse profile and spectrum were examined in greater detail, it became clear that Calvera could plausibly be significantly more distant at a few thousand light-years rather than a few hundred. At such distances, its observed flux implies an intrinsic luminosity similar to, or somewhat higher than those of the Magnificent Seven, and its position at high galactic latitude then places it far above the plane in the halo. The shift from a very nearby to a more distant interpretation changes the comparison with the Magnificent Seven. Instead of being simply another close thermally emitting neutron star in the local bubble, Calvera becomes an object whose thermal emission resembles that of these nearby stars in shape, but differs in context and in inferred distance. When temperatures are compared, Calvera appears somewhat hotter than most of the Magnificent Seven, though the precise values depend on the details of atmosphere modelling and on assumptions about magnetic field and surface composition. The Magnificent Seven typically show temperatures that correspond to a few 100,000 degrees Kelvin at their surfaces, while Calvera's best-fitting atmosphere models point toward an effective temperature that is higher consistent with a neutron star that is somewhat younger or that has cooled differently. This is in line with timing estimates of its characteristic age, which place it in the range of a few 100,000 years, comparable to or slightly younger than some of the nearby thermal emitters. In their spectra, both Calvera and the Magnificent Seven show deviations from pure blackbody curves. These deviations arise from the presence of an atmosphere and from the effect of strong magnetic fields on atomic transitions and particle motions. In several of the Magnificent Seven, broad absorption features appear at specific energies interpreted as proton-cyclotron lines, or bound-bound transitions in magnetized hydrogen. Calvera likewise shows evidence for at least one absorption feature in its soft X-ray spectrum, though its exact nature remains under study. The presence of such features in multiple thermally emitting neutron stars suggests that they share common surface physics, even if their field strengths and geometries differ. Another class of objects that provides a point of comparison is the central compact objects found in some supernova remnants. These are neutron stars located near the centers of young remnants in the galactic plane, often with soft thermal spectra and little or no detected radio emission. Like Calvera, they may show thermal emission that can be modelled with one or more hotspots on the surface superimposed on a cooler background. However, central compact objects are usually embedded in dense complex environments, surrounded by bright supernova debris and in some cases by faint nebulae. Their association with well-defined relatively young supernova remnants near the plane makes their locations and ages easier to constrain. Calvera, by contrast, sits in the halo and is associated, if at all, with a very faint and extended radio ring. The difference in environment means that Calvera's thermal emission is seen through a thinner column of interstellar material, while the surrounding remnant is far less conspicuous than the shells and filaments of many central compact objects. In addition, many central compact objects do not show strong pulsations, whereas Calvera's timing behavior clearly identifies it as a rotation-powered pulsar, a topic addressed more fully elsewhere in the narrative. Within the broader family of isolated neutron stars, there are also radio pulsars that show detectable thermal X-ray emission from their surfaces, often combined with non-thermal components from their magnetospheres. In many such systems, the thermal contribution is modest compared with the high-energy tail, especially at higher energies, but it can still be disentangled through spectral fitting. Calvera stands out among these in that its thermal component dominates the soft X-ray band, while non-thermal contributions are weak or absent in the observed range. This makes it more similar in spectral appearance to the Magnificent Seven than to the majority of rotation-powered pulsars, whose X-ray signatures are strongly non-thermal. The comparison highlights a blend of traits. Calvera is a rotation-powered pulsar with properties typical of that class in some respects, but its observed spectrum in soft X-rays more closely resembles that of thermally emitting radio-quiet neutron stars. When these groups are viewed together, Calvera occupies an intermediate position. It shares with the Magnificent Seven a dominance of thermal emission and a lack of strong non-thermal tails in soft X-rays, but it differs in location, likely distance and temperature. It shares with central compact objects an association tentative in Calvera's case, with a supernova remnant and a relatively soft spectrum, but it differs in that it lies in the halo rather than in the bright crowded plane. It shares with radio pulsars the status of a rotation-powered neutron star, yet it differs from many of them in how quiet it appears in radio and gamma rays, and in how prominent its thermal surface emission is. The net effect of these comparisons is that Calvera appears as a member of the thermally emitting neutron star family that has been displaced from the environments where such stars are usually found. Its halo location, its likely distance of several thousand light-years, and its temperature place it in a region of parameter space that is not heavily populated by other known objects. The broader population of thermally emitting isolated neutron stars provides a framework within which its properties can be understood. Its thermal luminosity and temperature are reasonable for a neutron star of its inferred age. Its spectrum behaves broadly as expected for a magnetized hydrogen atmosphere with modest hotspots, and its lack of strong non-thermal X-rays is not unique. What is unusual is the combination of these ordinary thermal traits, with an extraordinary position above the galactic plane, and with the detailed timing and multi-wavelength properties that will emerge in further layers of the analysis. In this sense, Calvera both resembles and differs from its closest kin, fitting comfortably into the general category of thermally emitting, isolated neutron stars, while occupying a comparatively rare corner of the distribution defined by location, environment, and observational behavior. Calvera's thermal emission gives one view of the star, but its rotation supplies another equally important layer of information. Careful timing observations of its soft X-ray light curve reveal that the flux from the star is not constant in time. Instead, it rises and falls in a regular pattern, repeating on a timescale of a small fraction of a second. By folding many individual X-ray photons according to their arrival, times astronomers find that the brightness varies with a period of about 59 thousandths of a second. This is the spin period of the neutron star, the time it takes for one full rotation. For a compact object only a few tens of kilometers across, such a short period means that the surface at the equator moves at a significant fraction of the speed of light. The pattern of pulsations indicates that the emitting surface is not uniform. There are regions that are slightly hotter or cooler than the average, so that as the star rotates, different parts of the surface come into and out of view, modulated further by the bending of light in the strong gravitational field. The result is a pulse profile in which the X-ray brightness rises smoothly to a peak and then declines again with the exact shape depending on energy and on the distribution of temperatures across the surface. The regularity of the pulses allows the spin period to be measured with high precision, and repeated observations show that this period is not perfectly constant over long timescales. Instead, it increases very slowly by a tiny fraction with each passing year. This gradual lengthening of the period is called spin down. It reflects the fact that the neutron star is losing rotational energy to its surroundings. Part of this loss is carried away in the form of electromagnetic radiation from the rotating magnetic field part in particle outflows, and part in any other processes that tap into the star's rotation. For Calvera, the rate of change of the spin period is small in absolute terms, but when combined with the period itself, it provides a powerful constraint on the star's properties. Astronomers often summarize the age implied by this spin down through a quantity known as the characteristic age. In simple terms, the characteristic age is obtained by taking the current spin period and dividing it by twice the rate at which that period is increasing. This ratio has the dimensions of time and serves as an estimate of how long the star has been slowing down under the influence of its breaking torque, under the assumption that its magnetic field has not changed drastically and that it was born spinning much faster than it does now. For Calvera, the measured period and its slow increase point to a characteristic age of a few 100,000 years. This places the star in a middle range between the very youngest neutron stars, which may be only a few thousand years old, and the much older recycled pulsars that are billions of years old. It is old enough that much of its initial heat has been radiated away, yet young enough that its surface temperature still lies in the range where thermal X-rays are bright. The same timing data used to derive the characteristic age also allow astronomers to estimate the strength of the star's dipole magnetic field at the surface. In the standard picture of a rotating magnetic dipole, the rate at which the star loses rotational energy depends on the square of the magnetic field, strength on the square of the radius, and on the fourth power of the rotation rate. By inserting Calvera's measured period and spin-down rate into this framework, and assuming a radius typical of neutron stars, one obtains a magnetic field strength of roughly a few 100 billion units in the usual field measure. Expressed in more everyday terms, this field is hundreds of billions of times stronger than the magnetic field at the surface of Earth. It is far below the extreme field strengths of magnetars, which can reach values 1,000 times larger, but it is comparable to those of many ordinary rotation-powered pulsars. In this sense, Calvera's field is strong but not exceptional within the neutron star population. The spin-down rate also encodes the total power that Calvera currently supplies to its surroundings through rotational energy loss. This spin-down power can be thought of as the rate at which the star's rotational kinetic energy decreases as it slows. For Calvera, this power lies within the range typical of middle-aged pulsars. It is high enough to sustain a magnetosphere that can in principle accelerate particles and produce emission in various bands, but not so high as to place the star among the most energetic young pulsars that drive spectacular nebulae and bright high-energy emission. This intermediate spin-down power aligns with the absence of a luminous pulsar wind nebula in the images and with the dominance of thermal emission in the soft X-ray band. From a purely rotational point of view, Calvera resembles many pulsars found in the galactic disk. Its period of a few hundredths of a second and its moderate magnetic field strength are common in surveys of radio and X-ray pulsars. The combination of period and spin-down rate places it on the familiar period-period derivative diagram where neutron stars occupy regions that reflect their ages and magnetic fields. Calvera lies in the portion of this diagram associated with relatively young rotation-powered pulsars that have not been spun up by accretion in a binary system. The absence of any binary companion in optical and X-ray data supports this classification. Its rotation is that of a remnant that has simply slowed under its own magnetic braking since birth, rather than one that has been recycled through interactions with a companion. The timing stability of Calvera's pulses is another noteworthy feature. Long sequences of observations show that aside from the steady spin down the arrival times of the pulses, follow a regular pattern that can be described by a smooth timing solution. There are no large sudden jumps in period or period derivative of the kind known as glitches, at least within the sensitivity and time span of current data. Glitches are thought to arise from changes in the coupling between the neutron star's solid crust and its superfluid interior, and their presence or absence can tell astronomers about internal physics. For Calvera, the observations so far suggest a stable rotator, although small glitches cannot be excluded without even longer monitoring. This stability helps in refining measurements of the spin-down rate and in searching for any additional periodicities or timing noise. The measured period and its derivative also place constraints on how much rotational energy Calvera has lost since its birth. If the star was born spinning much faster, as core collapse models suggest, then over hundreds of thousands of years, it has shed a large fraction of its initial rotational energy. That energy has gone into electromagnetic radiation and particle winds that once may have been more vigorous than they are now. The current spin-down power is the present rate of this loss, but it is only the latest chapter in a long history of breaking. The fact that Calvera's present period is still relatively short implies that even after this history, it remains a fast rotator compared with many pulsars with periods of a second or more. In summary, the timing properties of Calvera paint a picture of a neutron star that is globally ordinary but temporally young. Its spin period of about 59 thousandths of a second, its slow but steady spin down, and its inferred characteristic age of a few 100,000 years all place it in the class of middle-age rotation-powered pulsars. Its magnetic field strength derived from the same timing measurements is strong but not extreme, and its spin-down power is sufficient to drive a magnetosphere without producing the most dramatic high-energy phenomena. These rotational properties form a key layer in the multifaceted description of Calvera, linking its thermal surface emission to its internal energy reservoir and to the quiet loss of rotational energy that continues as it moves through the halo. The pulsations from Calvera carry more information than a single number for the rotation period. When astronomers examine the X-ray light curve in detail, they find that the brightness does not vary in a simple square wave or a narrow spike. Instead, the pulse profile has a smooth rounded shape with one main maximum and a broad minimum over each cycle. The exact form of this pattern depends on photon energy. At lower X-ray energies, the pulse contrast is moderate, with the brightness rising and falling by a limited fraction of the mean flux. At somewhat higher energies within the soft band, the pulsed fraction tends to increase, meaning that a larger share of the emission varies over the spin cycle, compared with the nearly constant component. This energy dependence indicates that the hotter regions on the surface contribute more strongly at higher energies, while the cooler, more uniform background dominates at lower energies. As the star rotates, the hotter patches move into and out of the visible hemisphere, modulated by light bending in the strong gravitational field. The relative strength of the pulses across the X-ray band therefore encodes the locations, sizes and temperatures of these hotter areas relative to the rest of the surface, as well as the orientation of the spin and magnetic axes with respect to the line of sight. When observers fit models to the pulse profile, they often find that a configuration with two hot regions near opposite magnetic poles superimposed on a cooler global surface can reproduce the observed behavior. In Calvera, the pulsed fraction reaches values of a few tens of % in the most favorable energy ranges. This is higher than in some thermally emitting neutron stars where the surface temperature distribution is more uniform, and suggests that the contrast between the hot spots and the cooler background is pronounced. The smoothness of the pulse shape without sharp spikes or deep notches also points to a relatively simple geometry, without narrow beams or abrupt eclipses. A further piece of structure appears when the spectrum is examined in fine energy bins. Around an energy of roughly 7/10 of a kilo-electron-volt, the data show a deficit of photons relative to the smooth continuum expected from the atmosphere model. This manifests as an absorption feature, shallow but statistically significant, that persists when different instruments and analysis methods are applied. The presence of this feature in the pulsed emission implies that its depth and shape can vary slightly with rotational phase, which in turn suggests that it arises in a region of the surface or magnetosphere that does not cover the entire star uniformly. Possible explanations include a cyclotron resonance associated with protons in the strong magnetic field, or a bound-bound transition in magnetized hydrogen in the outer layers, but the exact identification remains under discussion. Whatever its physical origin, the feature provides an additional diagnostic of the conditions near the surface, linking the detailed energy dependence of the light to the local field, strength and composition. While the X-ray pulsations are clear, and regular searches for corresponding pulsations at radio wavelengths have so far not yielded a detection. Radio telescopes have observed the position of Calvera at multiple frequencies, looking for periodic signals that match the measured X-ray period, or for dispersed pulses that would indicate a radio beam sweeping past Earth. These searches place upper limits on the radio flux density that are low enough to rule out a bright canonical radio pulsar at this location. In the catalogues of radio pulsars, many objects with periods and spin-down rates similar to those of Calvera produce detectable radio emission, yet Calvera itself remains undetected in radio bands. This combination of a clear X-ray pulsar and an undetected radio source motivates the description of Calvera as radio quiet or radio silent, at least within current sensitivity limits. There are several broad possibilities that can account for such behavior without invoking anything exotic. One is that Calvera does emit radio waves in a beam pattern similar to other pulsars, but the orientation of its magnetic axis and spin axis is such that the beam never crosses the line of sight to Earth. In that case, the pulsar would be intrinsically radio loud but observationally silent from this vantage point. Another is that the radio emission mechanism operates less efficiently in Calvera than in some other neutron stars, leading to a beam that is intrinsically weak or narrow, with a luminosity below current detection thresholds. In both scenarios, the absence of radio pulses reflects geometry and emission physics, rather than a fundamentally different kind of object. From the standpoint of direct observation, however, Calvera remains a star whose pulsations are revealed in soft X-rays, but not so far in radio light. Gamma-ray observations with space-based telescopes sensitive to high-energy photons add another layer. Many rotation-powered pulsars with periods of a few tenths of a second and magnetic fields of similar strength to Calvera's emit gamma rays that can be detected as periodic signals in instruments such as the Fermi Large Area Telescope. These gamma-ray pulsars often show light curves with one or more sharp peaks per rotation, and spectra that extend to high energies. For Calvera, analyses of gamma-ray data around its position and period have not yielded a firmly established periodic signal. Early claims of a candidate gamma-ray pulsation were later re-examined and did not hold up under improved data and analysis techniques. At present, there is no robust evidence for bright gamma-ray pulsations from Calvera, and upper limits on its gamma-ray luminosity place it at the faint end of what might be expected for a rotation-powered pulsar with its spin-down power. Again, this does not imply a qualitative difference in the underlying mechanisms. The emission geometry, the efficiency with which rotational energy is converted into gamma rays, and the alignment of beams relative to the line of sight all play roles. In Calvera's case, the combination of factors appears to produce a neutron star that is bright and regularly pulsed in soft X-rays, yet either faint or unfavorably oriented in radio and gamma rays. The multi-wavelength picture that emerges from these observational facts is that of a star whose thermal surface emission dominates the soft X-ray band, producing a pulse profile shaped by hotspots and gravitational light bending, while magnetospheric emission in radio and gamma rays is either weak or directed away from Earth. The timing solution derived from the X-rays anchors all of this behavior, providing a precise period and spin-down rate that connect the thermal and high-energy channels. The absence of detections in other bands serves as a set of upper limits on possible non-thermal components, giving astronomers boundaries within which models of the magnetosphere and beaming geometry must fit. In particular, the fact that the spin-down power is sufficient in principle to power detectable non-thermal emission, yet such emission is not observed at present places Calvera among the subset of rotation-powered neutron stars that are thermally bright, but radio-quiet and gamma-quiet. In such systems, the majority of the observable power at accessible wavelengths emerges from the cooling surface rather than from relativistic particles in the magnetosphere. For Calvera, whose halo location and possible association with a faint supernova remnant already set it apart in spatial terms, this pattern of pulsations and silence gives it a distinctive observational character. The star turns steadily its surface brightness, waxing and waning in soft X-rays with each rotation, while radio and gamma-ray instruments tune to the same period record no corresponding beat. The pulse profile in X-rays, the subtle absorption feature in the spectrum, the absence of radio and gamma pulsations and the measured spin-down rate together define a coherent layer of behavior in which Calvera appears as a young rotation-powered neutron star whose most accessible signature is a soft periodic glow rather than a loud broadband beacon. The surface of Calvera is not a featureless uniform sphere. Instead, it consists of a compact crust covered by a thin atmosphere whose properties vary with magnetic field strength, local gravity and temperature, and these variations create a map of conditions that shapes the observed X-ray pulses. In standard models for neutron stars like Calvera, the outermost layer is a magnetized hydrogen atmosphere, only a few centimeters to a few tens of centimeters thick. This layer is almost negligible in depth compared with the star's radius, yet it plays a crucial role in filtering and shaping the radiation that escapes. Photons generated in the hot crust and shallow layers below must traverse this atmosphere where they are scattered and absorbed by electrons and ions in the presence of a strong magnetic field. The field channels the motion of charged particles, making the atmosphere highly anisotropic. Its opacity depends on direction and on the polarization of the radiation, so that light emerging along field lines is affected differently from light emerging across them. At the same time, the surface gravity is so strong that pressure and density change rapidly, with height compressing the atmosphere into a thin shell where temperature and density vary sharply over a very short distance. Within this framework, the surface temperature of Calvera does not have a single value. The bulk of the star may sit at a relatively uniform effective temperature that declines slowly as the neutron star cools over hundreds of thousands of years. But magnetic fields and internal heat flow produce regions that are hotter or cooler than average. In particular, the magnetic poles where field lines pierce the surface more directly can act as channels for heat, allowing energy from deeper layers to escape more efficiently. These polar caps then maintain higher temperatures than the surrounding surface. The field also modifies thermal conductivity in the crust, favoring heat flow along field lines rather than across them, which further concentrates warmth near the magnetic poles and can suppress it in regions where the field geometry is more complex. The result is a temperature map in which two relatively small polar regions shine more brightly in X-rays than the cooler rest of the surface. Observations of Calvera's pulse profile support this picture. The modulation of the X-ray flux over each rotation indicates that at least part of the emission comes from discrete hot areas that sweep in and out of view. When theoretical models of a neutron star with two hot polar caps and a cooler global surface are adjusted to match the observed pulsed fraction and energy dependence, they reproduce many aspects of Calvera's behavior: the size of the caps, their temperatures relative to the rest of the surface, and their placement with respect to the rotation axis, all influence the shape of the pulses. If the caps are small and very hot, the pulses can be sharp and high in contrast. If they are larger or only moderately hotter than the background, the pulses become smoother and less extreme. Calvera's pulses sit in a middle range with a pulsed fraction of a few tens of % in the most sensitive bands, and a broad rounded profile consistent with polar regions that are hotter and somewhat confined but not tiny pinpoints of emission. The thin magnetized atmosphere on top of this temperature map further modifies the emerging radiation. Because opacities in the atmosphere depend on energy magnetic field and angle, the spectrum and intensity of the escaping light change with viewing direction. Radiation emerging near the magnetic poles where the field is strongest and more vertical may have a slightly different spectral shape and beaming pattern than radiation from equatorial regions where the field geometry is more tangential. In Calvera, the combination of such atmospheric beaming and the underlying temperature map produces an emission pattern that is not symmetric in all directions. To an observer at Earth, the brightness at a given rotational phase depends on how the line of sight cuts through this pattern, leading to the observed pulse profile. Relativistic light bending in the strong gravitational field smooths the modulation by allowing an observer to see more than half of the surface at once. Even when a hot polar cap rotates toward the far side of the star, some of its light still curves around, contributing to the flux at phases when in Newtonian geometry it would be hidden. This effect reduces the maximum pulsed fraction achievable for a given temperature contrast and cap size, but it also ensures that the contribution of the cooler surface is present at all phases. In models of Calvera, the interplay between light bending and atmospheric beaming is essential to matching the observed level of modulation. A cap that would produce a very strong pulse on a less compact star can generate a more moderate pulse when the light is bent by strong gravity. The subtle absorption feature in Calvera's spectrum near an energy of about 0.7 of a kilo electron volt likely arises within this same thin atmospheric layer or in a closely related region just above it. In a strong magnetic field, protons and electrons can move in quantized orbits, and atoms have altered energy levels. Transitions between these levels can create absorption lines at characteristic energies that depend on the field strength and on the composition of the atmosphere. If the feature in Calvera is a proton cyclotron line, for example, it would point to a particular magnetic field value at the surface. If it is a bound-bound transition in magnetized hydrogen, it would provide a different combination of constraints. In either case, the fact that the line appears on top of the thermal continuum and may vary slightly with rotational phase tells astronomers that it is tied to specific regions on the surface, perhaps the hotter polar caps where the local field and temperature differ from the rest of the star. The line depth and width then reflect the range of conditions across those regions. The atmosphere and temperature map also influence the relationship between Calvera's total thermal luminosity and its effective age. Standard cooling models for neutron stars predict how a uniform surface temperature should decline over time as the star loses internal heat through neutrino emission and photon emission from the surface. In practice, however, temperature anisotropies and magnetized atmospheres mean that the observed flux in a given band does not translate directly into a single global temperature. Instead, models must integrate over the entire surface, accounting for hot and cool patches and for atmospheric beaming. For Calvera, when this integration is carried out using atmosphere models that fit the spectrum and pulse profile, The inferred global luminosity lines up reasonably well with expectations for a neutron star of a few 100,000 years, though uncertainties in distance and magnetic field geometry leave some room for variation. The key point is that the atmosphere and temperature map bridge the interior physics of cooling and heat transport with the observable X-ray emission at the surface. In the presence of a strong magnetic field, heat flow from deeper layers is guided in patterns that create the hot polar caps and cooler equatorial areas. The thin magnetized hydrogen atmosphere then shapes the spectral and angular distribution of the outgoing photons, imprinting subtle features and beaming patterns. Finally, gravitational light bending modifies how all of this appears to a distant observer. Calvera's observed thermal pulses, spectrum and subtle line feature are the visible traces of this layered structure. On the scale of the surface, the neutron star is a patchwork of temperatures and field strengths rather than a uniform sphere, and the atmosphere acts as a semi-transparent screen that translates that hidden map into the soft X-ray glow that telescopes record. Through detailed modelling, astronomers use these observations to reconstruct as far as possible the arrangement of hot and cool regions on Calvera and the properties of the atmosphere that covers them, building a coherent picture of the star's outermost layers before turning inward to the deeper crust and core that underlie them. Beneath the thin magnetized atmosphere and the patterned temperature map on Calvera's surface lies a solid crust and a series of deeper layers that together hold most of the star's mass and govern much of its long-term evolution. Moving downward from the atmosphere, the density of matter rises very quickly. In the outer crust, atoms are so strongly compressed that their electrons form a degenerate gas, filling all available low-energy states, while the atomic nuclei themselves arrange into a crystalline lattice. The nuclei in this region are much heavier than those found in ordinary matter, consisting of many protons and neutrons squeezed into compact clusters, and the lattice supports a rigid structure that can transmit shear stresses. This outer crust extends over a distance that is small, compared with the star's radius perhaps on the order of a kilometre or less. Yet it provides the mechanical framework that supports any small deviations from perfect sphericity on the surface. Tiny irregularities, sometimes referred to as mountains, in a loose sense may be only millimetres high, but in the immense gravity of a neutron star they carry significant stresses. Deeper still, at densities higher than those in the outer crust, neutrons begin to drip out of the nuclei and form a fluid that coexists with the nuclear lattice. This marks the inner crust where the matter becomes a mixture of nuclei degenerate electrons and a sea of free neutrons. The neutrons in this region are thought to form a superfluid, a state in which they flow without viscosity and can sustain quantized vortices that carry angular momentum. The presence of this superfluid component has important consequences for the star's rotation and for possible glitches, although in Calvera no large glitches have yet been observed. The coupling between the superfluid and the solid lattice can in other neutron stars lead to sudden changes in spin when pinned vortices are released. Even if such events have not been detected in Calvera, the same basic structure of crust and superfluid is expected to be present because it arises from general considerations of dense matter rather than from specific observational quirks. In this layered crust, the magnetic field of the neutron star threads through both the solid lattice and the superfluid. The large-scale dipole component that governs the spin-down and beaming geometry is anchored partly in the crust and partly in the deeper interior, while smaller scale field structures can be concentrated in the outer layers. Over time, electrical currents that support these fields evolve through processes such as ohmic decay and Hall drift. In a star with an age of a few 100,000 years, as Calvera appears to be, these processes may have altered some small-scale features of the field, but are not expected to have erased the global dipole. This is consistent with the timing measurements which indicate a magnetic field strength typical of ordinary rotation-powered pulsars. The same field that shapes the magnetosphere and the surface temperature map also channels heat flow through the crust, guiding energy from the deeper interior toward the polar caps more efficiently than toward equatorial regions. This combined influence of field topology and crustal composition ties the behavior of the observable surface closely to the unseen layers below. Below the inner crust, conditions change again as the last remnants of the nuclear lattice dissolve. In the outer core, matter is thought to exist as a uniform fluid of neutrons, with a smaller fraction of protons, electrons, and possibly muons mixed in. The neutrons in this region are also expected to form a superfluid, while the protons may form a type of superconductor. In such a state, the magnetic field may be organized into quantist flux tubes that thread the superconducting proton fluid, while the angular momentum of the star is carried partly by quantized vortices in the neutron superfluid. The interaction between these vortices and flux tubes can influence both the long-term evolution of the magnetic field and the star's rotational dynamics. Although direct evidence for these microphysical details in Calvera is beyond current observational reach, general neutron star theory and observations of other systems suggest that this combination of superfluidity and superconductivity is a common feature. It shapes the rate at which the star cools, the way it responds to stresses, and the evolution of its magnetic field over hundreds of thousands of years. At even greater depths in the inner core, densities can rise to several times those found in atomic nuclei. Here, the exact composition of matter is less certain. Different theoretical models propose that the core could consist of extremely dense nuclear matter, with exotic particle species such as hyperons or even deconfined quark matter in some form. Observations of neutron star masses, radii, and cooling behavior place constraints on these possibilities, but no single model has yet been conclusively verified. For Calvera, the combination of its inferred mass and radius, which appear to be within typical neutron star ranges, and its temperature at an age of a few 100,000 years, do not demand any especially exotic core composition. Its thermal luminosity and cooling rate are compatible with standard cooling scenarios, in which neutrino emission from dense nuclear matter dominates the early evolution, followed by a phase in which photon emission from the surface plays a larger role. In the early life of a neutron star, neutrino emission from the core carries away heat, rapidly causing the interior temperature to drop on timescales of tens of thousands of years. As the star ages, this neutrino cooling slows, and the crust and core temperatures approach a more gradual decline. At ages of a few 100,000 years, the surface temperature that observers infer from X-rays depends on how efficiently heat is transported from the core to the crust and then through the atmosphere. The presence of superfluid and superconducting phases in the core can modify neutrino emission through processes such as Cooper pair formation, leading to characteristic features in the cooling curve. If Calvera's core has properties similar to those in standard models, the observed surface temperature and luminosity are consistent with a neutron star that has cooled in a relatively ordinary way without strong evidence for extreme rapid cooling or for unusual heating mechanisms. The magnetic field crust and core together form a coupled system. Stresses in the crust caused by the evolution of the magnetic field can slowly rearrange the field lines, while changes in the field can alter how heat flows through the crust. Sudden adjustments in this coupled system could in principle produce bursts or glitches, while slow adjustments can lead to modest changes in pulse profiles and surface temperature distributions over long timescales. In Calvera, the observed stability of its timing and the steadiness of its thermal emission suggest that during the span of current observations, no large-scale crustal reconfiguration has taken place. Instead, the star appears to be in a relatively quiet phase of its evolution, with the interior structure settled and the crust supporting a stable pattern of magnetic and thermal anisotropy. Even in this quiet state, the interior layers remain crucial. They store the bulk of the star's thermal energy and determine how quickly that energy is released. They define the moment of inertia that enters into the spin-down calculations, and they contain the superfluid and superconducting phases that can, under the right conditions, produce observable timing irregularities. For Calvera, the interior is inferred rather than directly seen, but its influence is evident in the overall consistency of the cooling picture, in the timing properties that reflect a stable moment of inertia, and in the surface pattern that requires magnetic and thermal structures rooted in the crust and core. In this layer of the narrative, Calvera is understood not only as a hot surface and a measured period, but as a stratified object whose crust magnetic field and dense core work together to produce the quiet, steady emission and rotation that observers now measure in the halo of the galaxy. The motion of Calvera across the sky adds another layer to the picture of a neutron star that now resides in the galactic halo. Over timescales of years, its position shifts slightly with respect to distant background sources. This apparent drift, known as proper motion, is measured in small angles per unit time and reflects the component of the star's velocity that lies perpendicular to the line of sight. For nearby stars, proper motion can be relatively large and easy to see over decades, but even for objects at distances of many hundreds or thousands of parsecs, high-precision X-ray and optical astrometry can reveal motions of only a few tens of milliseconds per year. In the case of Calvera, long-term monitoring with high-resolution X-ray instruments, such as the Chandra high-resolution camera, combined with the precise timing position from NICER observations, has produced a measurement of proper motion that is both significant and well-constrained. The star's position shifts by an amount corresponding to roughly 8 arcseconds per century, or about 80 milliseconds per year, along a direction that on the sky points roughly away from the center of the faint radio ring that surrounds it. This rate of motion is tiny when expressed as an angle, but becomes substantial when translated into a physical velocity at plausible distances. To connect the proper motion to a tangential speed, astronomers multiply the angular rate by the distance to the star. For Calvera modelling of its X-ray emission and the lack of a bright optical counterpart argue for a distance that is likely at least of order 1,000 parsecs and possibly a few times larger, although an exact value remains uncertain. At a distance of around 1,000 parsecs, a proper motion of roughly 80 milliseconds per year corresponds to a tangential velocity of several hundred kilometers per second, on the order of a few hundred kilometers per second when expressed with more specific numbers. If the star sits at a greater distance, the tangential speed scales upward, remaining in the broad range characteristic of neutron stars that have received a natal kick from a supernova explosion. Velocities of a few hundred kilometers per second are common among pulsars reflecting the asymmetric forces at play during core collapse. Calvera's measured proper motion therefore indicates that it is not moving lazily through the halo, but instead travels with a speed consistent with a remnant that has been given a substantial impulse at birth. The direction of that motion is as important as its magnitude. When the proper motion vector of Calvera is plotted on the sky and extended backward in time, it points toward the geometric center of the large radio ring identified around the star. Within the uncertainties of the measurement and the ring geometry, Extrapolating the path backwards by a time of order, 10,000 years brings the star close to the centre of the shell, while extrapolating forward shows it moving steadily away. This geometrical alignment strengthens the interpretation of the ring as a supernova remnant associated with Calvera, and suggests that the neutron star was born near the centre of the shell and has since drifted outward under the influence of its natal kick and the gravitational potential of the galaxy. In this view, the offset between the current position of the pulsar and the centre of the radio ring is not a coincidence, but the natural outcome of a finite age and a measurable transverse speed. The proper motion measurement also allows astronomers to separate, at least conceptually, the different components of Calvera's velocity. The tangential component derived from proper motion and distance lies in the plane of the sky and contributes to the observed drift against background sources. The full space velocity also includes a radial component along the line of sight, which is harder to measure directly for an X-ray source without a clear optical counterpart. Without a radial velocity, the three-dimensional motion cannot be completely reconstructed, but plausible ranges for this missing component can be considered. For reasonable values, the total space velocity still falls in the several hundred kilometers per second range, consistent with a strong kick at birth. The direction of a motion on the sky when translated into galactic coordinates has a component that carries Calvera gradually farther from the centre of its surrounding ring, and a component that affects its height above the galactic plane. At a galactic latitude of about plus 37 degrees and a distance of around 1 to a few thousand parsecs, Calvera already sits hundreds to more than 1,000 parsecs above the plane. The vertical component of its velocity, whatever its exact value, will determine how this height changes over time. If the star was born in the halo at roughly its present height, its motion may keep it on an orbit that oscillates above and below the plane with a relatively large amplitude. If it was born closer to the thin disk and later reached its current altitude, the combination of present height and present velocity implies a significant journey through the galactic gravitational potential. In either case, the measured proper motion shows that Calvera is not stationary with respect to the halo gas and the remnants of its own explosion. It moves through the interior of the radio shell and the surrounding hot plasma, gradually shifting from the inner regions toward the outer parts of the remnant and in time beyond its boundaries. In simple terms, the star is now near the center of a large bubble, but slowly heading toward one side, tracing a path that future observations could follow as the offset grows. The timescales involved are long relative to human lifetimes, but modest on galactic scales. Over 10,000 years, a tangential velocity of a few hundred kilometers per second corresponds to a displacement of a few parsecs, which at a distance of around 1,000 parsecs subtends an angle comparable to the observed offset between Calvera and the center of the radio ring. Over hundreds of thousands of years, similar velocities can carry a neutron star many hundreds of parsecs away from its birthplace, enough to move it from the thin disk into the halo, or to shift its position within the halo by a substantial amount. For Calvera, the combination of its current height, its measured proper motion, and the apparent association with a high-latitude supernova remnant suggests that much of its displacement from any original star-forming region may have occurred at or near its present altitude rather than entirely as a climb from the disk. In the context of the wider halo environment, Calvera's motion can be imagined as a steady track through a low-density medium. The hot plasma inside the remnant forms a diffuse background that exerts little drag on the neutron star, whose mass and compactness make it largely immune to hydrodynamic forces at the densities involved. Instead, its path is governed primarily by gravitational forces from the Milky Way, and by the initial momentum imparted during the supernova. The star's passage through the halo gas can nevertheless produce subtle signatures such as a very faint bow shock if its speed relative to the local sound speed is sufficiently high, but no such feature has yet been clearly identified around Calvera. In observational practice, the most direct evidence of motion remains the shift in celestial coordinates measured over repeated X-ray observations. The precision of these measurements improves as the time baseline grows, so that future data may refine the proper motion, further narrowing the range of allowed distances and velocities when combined with models of the remnant and the halo potential. At present, however, the existing proper motion already plays a crucial role. It ties the neutron star's path to the center of the radio ring, supports the picture of a high-latitude supernova that created both the shell and the pulsar, and situates Calvera among neutron stars with significant natal kicks. In this layer of the narrative, Calvera is seen not only as a point source at a fixed coordinate, but as a moving object tracing a line across the halo sky, its proper motion recording the momentum it received in a distant explosion, and its velocity carrying it gradually outward through the sparse gas and the fading boundaries of its own supernova remnant. The present state of Calvera, with its soft thermal X-rays, rapid rotation and position high in the galactic halo, invites questions about how it is born and how it cools to the temperature now observed. One natural starting point is the idea that Calvera forms where it is now seen in a supernova explosion that occurs directly in the halo rather than in the thin disk. The faint radio ring that surrounds the neutron star and the diffuse high-energy plasma inside that ring suggest that a core collapse event took place in this high-latitude region, carving out a large low-surface brightness shell in the thin halo gas. In this picture, a massive star lives and dies in the halo itself, leaving behind both the extended remnant and the compact core that spins today as Calvera. The alignment between the neutron star's proper motion and the geometric center of the ring, together with the consistency between the shell size and the expected expansion in a tenuous medium, supports this scenario. If the ring is indeed a supernova remnant, then the time needed for the shell to grow to its current dimensions in a low-density halo environment sets an approximate age for the explosion. Models of remnant evolution in such conditions typically yield ages of tens of thousands of years for shells of this size, depending on the energy of the explosion and the ambient gas density. This age range is somewhat smaller than the characteristic age inferred from Calvera's spin down, which lies in the domain of a few 100,000 years. The difference between these timescales forms one of the tensions that motivate the statement that Calvera should not exist in such a location, at least under very simple assumptions. A naive picture in which a neutron star's characteristic age is taken as a precise clock, and the remnant shell is interpreted using a single density and energy would make it difficult to reconcile a young explosion age with a much larger spin-down age. However, both age estimates carry uncertainties. The characteristic age assumes that the breaking torque on the star and its magnetic field have remained constant over time, and that the initial spin period is much shorter than the current one. If Calvera is born with a period not much smaller than the present value, the characteristic age can overestimate the true age by a significant factor. Similarly, the remnant age depends on the unknown explosion energy on the density and structure of the halo gas, and on the stage of evolution that the shell has reached. Variations in these parameters can alter the apparent remnant age by factors of a few. Within these uncertainties, a scenario in which Calvera forms in a halo supernova within the ring, and then evolves over tens to a few 100,000 of years toward its current rotation and thermal state, remains possible without invoking unusual physics. An alternative birth path takes the progenitor star from the galactic disk into the halo before it explodes. In this case, a massive star forms in the thin disk, perhaps in a spiral arm or a star-forming region, and then receives a strong kick, or is ejected dynamically from a cluster or binary system. Its space velocity carries it away from the birth site and into higher latitudes. If the star is sufficiently massive, its lifetime before core collapse is relatively short, on the order of a few million years. During that time, a high-speed runaway can travel hundreds or even 1,000 parsecs away from the plane, reaching halo heights, similar to Calvera's present position. The subsequent supernova then occurs not in the dense disk but in the thinner halo gas, creating a remnant shell and a neutron star that both begin their lives far above the plane. In this runaway scenario, Calvera's current height and proper motion reflect the combined motion of the progenitor and the remnant. Depending on the direction and strength of the natal kick imparted at core collapse, the neutron star's trajectory may not align exactly with that of its parent, but the existence of a halo explosion remains compatible with a progenitor that originates in the disk. The net result is similar to the first scenario. A high-latitude supernova produces a shell and a neutron star in the halo. The difference lies in where the progenitor spends its main sequence life, and in how long it travels through the galactic potential before the explosion. Both possibilities, in situ halo formation and disk runaway, require that at least one massive star reach the region of the halo, where the remnant and Calvera are now observed. Observationally, massive stars are rare at such heights, but not impossible, especially if runaway mechanisms are efficient in some clusters or binaries. Whichever path is followed, the supernova deposits energy into the halo gas, inflating the faint radio ring and heating the plasma that glows in X-rays, while the core collapses into the neutron star whose cooling now dominates the soft X-ray emission. Once formed, Calvera begins its thermal evolution as an extremely hot compact object. In the immediate aftermath of core collapse, its interior temperature reaches values at which neutrino emission from dense matter is the dominant cooling channel. Over the first tens of thousands of years, neutrinos carry away the bulk of the thermal energy, reducing the internal temperature by orders of magnitude, while the crust and atmosphere adjust to the changing conditions. Different theoretical models of the dense matter equation of state and of superfluid and superconducting phases in the core predict different neutrino emissivities and therefore different cooling rates. In some scenarios, enhanced neutrino processes lead to very rapid cooling, bringing the surface temperature down quickly, while in others slower. Neutrino emission allows the star to remain warmer for longer. As the neutron star edges beyond this early neutrino-dominated phase, photon emission from the surface in X-rays and other bands becomes increasingly important. The cooling curve, which relates surface temperature to age, then flattens somewhat, and the star's thermal state at a given time depends on a combination of its mass, its internal composition, the presence and strength of superfluidity, and the properties of the outer layers. In standard cooling models for neutron stars of typical mass and composition, a star with an age of a few 100,000 years has a surface temperature that lies in the range inferred for Calvera when atmosphere models are applied to its spectrum. Its thermal luminosity at this age also falls in the range observed for Calvera when plausible distances are assumed. These agreements suggest that Calvera does not require an extreme cooling mechanism or a strong additional heating source to reach its present thermal state. Instead, it behaves broadly as a neutron star that has cooled according to relatively ordinary physics, with neutrino emission dominating early and surface photon emission governing the later evolution. The presence of hot polar caps superimposed on a cooler surface adds some structure to this picture, but does not change the global luminosity significantly. The temperature anisotropies arise from magnetic field-guided heat transport and from any ongoing heating in the outer crust, such as that associated with returning magnetospheric currents at the polar caps, while the average surface temperature still tracks the interior cooling. Within this framework, the main puzzle is not that Calvera is too hot or too cool for its characteristic age, but that such a thermally emitting rotation-powered neutron star appears in the halo rather than in the disk. The cooling models that fit its present temperature at its inferred age are the same models that describe many neutron stars born in the plane. The unusual feature is the spatial context, which must be explained by the birth scenarios and kinematic paths rather than by radically different thermal physics. In both the halo explosion and runaway progenitor scenarios, the combination of remnant size halo environment, proper motion, and spin-down age sets up a range of acceptable ages and cooling trajectories that keep Calvera within the envelope of standard cooling curves. The softness of its thermal X-rays, the absence of strong non-thermal components, and the relatively low interstellar absorption along the line of sight all help observers read this cooling history more clearly than in many other systems. The faint radio ring and the hot plasma around it mark the energy that the original supernova deposited into the halo gas, while the neutron star's present temperature and luminosity reflect the energy that remains stored in the compact remnant and is now radiated away quietly in soft X-rays. In this way, Calvera's birth scenario and cooling history tie together the large-scale structure of the halo environment, the intermediate scale of the supernova remnant, and the small-scale physics of dense matter in the interior without requiring any departure from the broadly accepted framework of neutron star formation and cooling, even as its location and age combination continue to mark it as an uncommon example within that framework. Seen against the full population of neutron stars in the Milky Way, Calvera occupies a position that is both consistent with general expectations and unusual in specific combinations of its properties. Population models for neutron stars start from the distribution of massive stars in the galactic disk, the rates of core collapse supernova, and the range of natal kick velocities imparted to remnants at birth. In these models, most neutron stars form near the galactic plane and are born spinning rapidly with strong magnetic fields. Over time, they spin down under magnetic braking and move through the galactic potential on orbits determined by their initial velocities and the galaxy's mass distribution. The majority remain within a few hundred parsecs of the plane for many millions of years, while a subset with particularly large kicks or favorable trajectories reach greater heights and enter the thick disk or the halo. When synthetic populations generated in this way are compared with observed samples of radio pulsars and thermally emitting neutron stars, they reproduce broad features such as the concentration of young pulsars near the plane, the existence of radio-quiet, thermally emitting objects at modest distances, and the presence of a smaller number of high-velocity remnants that have migrated to larger latitudes. In these frameworks, Calvera can be placed on diagrams that relate spin period, derivative magnetic field, and age alongside thousands of other neutron stars. Its measured period of about 59 thousandths of a second, and its spin-down rate yield a magnetic field, strength and characteristic age that place it in the region associated with middle-aged rotation-powered pulsars that have not been recycled in binaries. In this sense, Calvera sits in a well-populated part of the period derivative plane. The values of its inferred magnetic field and spin-down power are unremarkable for a neutron star of its kind. Many radio pulsars in the galactic disk share similar rotational properties and characteristic ages. Its thermal luminosity and surface temperature, when modelled with magnetised atmosphere fits and plausible distances of a few thousand parsecs, also fall within the envelope predicted by standard cooling curves for neutron stars of typical mass at ages of a few 100,000 years. These ordinary placements within rotational and cooling parameter spaces emphasize that on the level of intrinsic stellar properties, Calvera is not an outlier. It appears to obey the same microphysical laws of dense matter, magnetic field evolution and neutrino cooling that govern other neutron stars. The aspect that makes Calvera distinctive emerges when these otherwise ordinary properties are combined with its location high above the galactic plane and its observational classification as a thermally emitting radio-quiet X-ray pulsar in the halo. Population synthesis studies that track the vertical distribution of neutron stars typically predict that the vast majority of young thermally bright neutron stars should still lie close to the plane, because their ages are too small to allow extensive vertical motion under the galaxy's gravitational pull, even with strong kicks. Objects with characteristic ages of a few 100,000 years and moderate velocities generally reach heights of a few hundred parsecs, while those that travel to kiloparsec scale heights are rarer and often older. In such models, the probability of finding a neutron star with Calvera's apparent age and thermal brightness at its inferred height is not zero, but it is small compared with the probability of finding similar objects in the disk. Calvera therefore occupies a part of the combined space of age height and luminosity, where only a thin tail of the population is expected. Its presence in this tail is not impossible, but stands as a valuable test of the assumptions that enter the models, such as the distribution of kick velocities, the structure of the galactic potential at high latitudes, and the birth locations of progenitor stars. Another angle from which to view Calvera's place in the population is through the classification of isolated neutron stars by their emission properties. Rotation-powered pulsars with similar periods and magnetic fields often show strong radio emission and in many cases detectable gamma rays. A subset, however, appears radio quiet and is detected primarily in X-rays, either through non-thermal magnetospheric emission or, as in Calvera's case, through thermal surface emission. Thermally emitting isolated neutron stars like the Magnificent Seven, which are nearby and radio quiet, occupy one part of this classification space. Central compact objects in supernova remnants occupy another, and rotation-powered pulsars with strong non-thermal X-rays and gamma rays occupy a third. Calvera sits at an intersection of these categories. It is clearly a rotation-powered pulsar as shown by its spin period, and spin down, yet its X-ray spectrum is dominated by thermal surface emission, rather than by a strong non-thermal tail. It lacks confirmed radio and gamma ray pulses, placing it among the radio-quiet and gamma-quiet subset. Its thermal emission resembles that of the Magnificent Seven in shape, but differs in inferred distance and environment, as it is not a nearby object in the local bubble, but rather a more distant one in the halo. It has a possible supernova remnant association like central compact objects, but that remnant is faint large and located at high galactic latitude. In population terms, Calvera therefore represents a convergence of several pathways, a rotation-powered pulsar whose beaming and magnetospheric efficiency yield little observable radio or gamma radiation, a thermally bright neutron star whose cooling keeps it luminous in soft X-rays at its age, and a remnant that through its birth scenario and motion finds itself in the halo rather than in the disk. Current catalogues likely contain other neutron stars with one or more of these traits, but Calvera's particular combination remains rare, This rarity is reflected in the observational fact that only one such object has so far been identified in the halo with these specific properties. Population models can be adjusted to ask how many Calvera-like objects should exist in the galaxy at any given time. By folding in the rate of core collapse supernovae, the distribution of kick velocities, the fraction of neutron stars that are radio quiet, or have beams that do not cross Earth, and the cooling curves that determine how long a star remains thermally bright, one can estimate the expected number of halo neutron stars that are both young enough and luminous enough in soft X-rays to be detectable in current surveys. These calculations suggest that some halo neutron stars should be visible, but their numbers are small, and their detection is challenging because of survey sensitivities and the need for wide coverage. Calvera fits comfortably within the range of one or a few such objects that might be found in existing data. Its discovery therefore does not overturn the broad predictions of population synthesis, but it provides an important data point for refining them, especially in the high-latitude regime. In terms of the statement that Calvera should not exist, the tension lies not in any violation of fundamental physics, but in the discrepancy between first-order expectations and detailed reality. A naive expectation might be that middle-aged thermally bright neutron stars should be confined close to the galactic plane, with only older, cooler and fainter stars occupying the halo. Calvera contradicts that oversimplified picture by showing that a relatively young, thermally luminous neutron star can be found at high latitude. More refined models that take into account the full distribution of kicks, the possibility of halo or thick disk progenitors, and the range of cooling histories show that such objects are rare, but allowed within the tail of the distribution. In this refined view, Calvera does not break the rules. It occupies a position that tests how well the rules capture the outer edges of the population. Several open questions remain when Calvera is viewed in this population context. One concerns its exact distance, which influences both its inferred height above the plane and its thermal luminosity. Improved constraints on distance, whether through better modelling of its atmosphere, more precise measurements of interstellar absorption, or future parallax observations if an optical counterpart becomes measurable, would sharpen its placement in the age-height luminosity space. Another involves the detailed structure and age of the surrounding radio ring and hot plasma, which feed back into estimates of the supernova explosion energy, ambient density and remnant evolution. Clarifying the relationship between the remnant and the neutron star would help fix the true age of the system and refine comparisons with cooling curves. A third concerns the reasons for Calvera's radio and gamma quietness relative to other pulsars with similar spin-down parameters. Whether this reflects beaming geometry, intrinsic emission efficiency, or subtler magnetospheric properties remains an area for further theoretical and observational study. As more sensitive surveys of the sky and X-rays radio and gamma rays accumulate data, additional thermally emitting high-latitude neutron stars may be discovered. Each new object would provide another point in the distribution, helping to determine whether Calvera is one of many similar remnants or a member of a small rare class. For now, it stands as a well-characterized example of a halo neutron star whose rotation, thermal emission, and proper motion can all be measured. In the context of neutron star population models, Calvera is a reminder that the galaxy's inventory of compact remnants includes not only the numerous pulsars in the disk and the nearby thermally emitting stars, but also a more sparsely populated halo of neutron stars that have received strong kicks or have had birth paths that carry them far from familiar star-forming regions. Among these, Calvera is one of the clearest cases so far. Its soft X-ray pulses and quiet multi-wavelength behavior offering a steady signal by which the outer reaches of neutron star populations can be explored.